In this section, we're going to jump into how to do MPC in the context of PySyft and really walk through the base core primitives that are actually implemented in an MPC protocol so that you can sort of understand what's available and how higher level things are constructed on top of it. So the first thing we want to do is kind of do our normal Syft boilerplate. So import Syft as sy, import torch as th, and then we want to set our hook. So if you remember from before, this is actually what overloads torch all the MPC protocols that we care about. From torch, import in optim. Great. We just need those for later. Okay, now we want to create a couple workers. So we'll say Bob is a virtual worker. Hook ID equals Bob. Just make sure that it knows about the local worker. Then Alice equals virtual worker. Sometimes these are propagated automatically, but sometimes they're not. I just want to make sure it's in there because we'll actually need these workers to communicate directly with each other. So it's good to check. Cool. Groovy. All right, so now let's create some data. Do some other random values here. And let's check out the API. So if I go x equals x.share Bob Alice, and then crypto provider equals secure worker. So now, a few intuitives. Bob and Alice each have a share of x. The crypt provider is basically responsible for reliably generating random numbers. Now, for most protocols, this is not, or at least these protocols we have implemented, this is not strictly speaking a requirement, but it does increase performance significantly. Like there are versions of these protocols that allow you to just do things between Bob and Alice. But for the purpose of sort of getting the fastest performance out of deep learning system, we choose to implement them with a crypto provider. And so this secure worker is just, it's assumed to not be Bob or Alice. We sort of trust them to not collude with either of them in the same way that we trust Bob and Alice not to collude with each other. Yeah, so it can really be anyone. It's just sort of, we just trust them to sort of reliably generate random numbers and distribute them correctly according to the protocol, which we tell them to. So there you go. All right, and so here we go. So now what can we do? So something you already should know is x plus y equals z. So obviously, this already works. So you should be already quite familiar with this because we used this for secure aggregation before. Also implemented is subtraction. So using the way that we mentioned in an earlier message. But now we also have encrypted multiplication. And so this uses an algorithm called speeds. Which is one of the fastest algorithms for being able to do secure MPC based multiplication. And the nice thing is that this is implemented under the hood, and we could jump into exactly what speeds is, but at this point it's just important for you to understand how the numbers are encoded, which you already understand from the addition and multiplication examples, and understand that there is a cryptographic protocol with which these different shareholders are communicating with each other to make this possible, right? And that the core assumption is that you're trusting that they don't collude with each other, or the subgroups don't collude with each other to try to decrypt different components. Cool, let's keep going. So the next one that we have is the comparison operator. Now the comparison operator is from an algorithm that was published last May, which is called SecureNN, and was specifically built to do ReLU operations in the context of neural nets very, very efficiently. A ReLU operation is obviously a comparison operation, so we've implemented it here in this tensor type as a simple comparison operation. The nice thing is once you get one comparison operation, you can also get all of the rest of them. So we have equals, right? So as you can see, we have tensor-based operations that implement secure MPC amongst these different shareholders, right? So Bob, Alice, and then leveraging the crypto provider for our random number resources. And actually, the crypto provider is temporarily a shareholder for the SecureNN protocol. But again, the trust assumption is still the same. You're trusting that the crypto provider isn't colluding with Bob or Alice. And the nice thing is that the crypto provider can be literally anyone. So finding someone on the planet that is, not biased towards Bob or towards Alice specifically is a reasonable task. That we feel that it is, and that's why we implemented the protocol in this particular way, and it significantly increases the performance of the operations we can do. However, we cannot just do these on integer tensors like we have here. We can also do them on fixed precision tensors. So if you remember from before, so if I said, we'll just copy this down here again, and instead of just sharing it, if I say x dot fixed precision, and then share, and then y equals y dot fixed precision, and share, then we can still do the same stuff. And there you go. So all these same operations work on decimal numbers as well as integers. Just to show you. Now the interesting thing to note here for comparison, float precision is always going to return a floating point, but it's still this kind of 0-1 mask, right? So for the comparison operation, and I suppose I didn't enumerate this before, when it's true, it returns a 1 in that place value, and when it's false, it returns a 0. And this is basically very, very useful for being able to do things like Boolean logic and circuits, and you can use these as masks and lots of sort of interesting ways to do this. It's very similar to how PyTorch does this natively, actually, and NumPy as well. Often they might not return it as a floating tensor. Different tensor libraries do that, and actually have done it differently in different versions. But as long as you know this is how it's returned, you can sort of build your code logic appropriately. But yeah, so that's how this works. So x, obviously doesn't equal y. So if we did x equals x, obviously they'd all be 1. And yeah, so there you go. So this gives us a base API for encrypted computation. As it turns out, if you can do addition and multiplication, you can actually do Turing complete sort of style computation. Comparison gives us actually easier. You can do any polynomial, obviously, with addition and multiplication, which allows you to do most anything you want. The comparison operation allows us to do some things quite a bit more efficiently, and perhaps with less code. And so yeah, these are the core primitives that we've implemented in Secure MPC, and other things we have built on top of that. Now there are also some things that you get sort of for free, right? So if this is our tensor, we can also use indexing and slicing, for example, which we get out of the box. And the reason we get this is just because each number is Secure MPC shared by itself, right? So we get this, we get the transpose operations, we get concatenation, all the kind of indexing based operations happen out of the box, but those don't really require a special Secure MPC protocol. That's just about sort of moving shares around and sort of inverting the tensors or doing whatever you need to do. But yeah, as far as things that actually involve changing the values and computing functions on the values, these are the core primitives that we work with, and we build things like ReLU or Sigmoid or TANH kind of on top of these core primitives. And so speaking of building things on top of these core primitives, in the next video, we have a very fun project, which is not deep learning related, but it's a little bit simpler, where we work with one way that we can use these primitives to build kind of a cool little project. So I'll see you in the next video.